Hello guys, this is my presentation for assessment 2 of SIT 718 real world analytics. In this presentation I will show how I have took the wine data and transformed it into normal data and then use the best predicting model to predict the score of the particular wine set. So first we'll start with the raw data distributions. So variable 0, the citric acid, is like this data, and as we could see from the distribution graph, the data is not normally distributed as I have done a normality test using Shapiro-Wilk test, and it's not, the p-value is not reasonable. Along with that we could see the data is moderately skewed, and even if we see the QQ plot, I would say the data is lightly tailed towards the left part, and that we could see from the frequency graph as well. After that, we will go to the chlorides data set. From that we could see the skewness is 5. It means the data is positively skewed, and which we could see from the frequency graph. And when we do the normality test on it, the p-value is not significant and we can't do the null hypothesis. And if we see the QQ plot, we could also see that from the QQ plot the data is tailed towards the end part of the data set. And if we go to the next variable, which is sulfur dioxide, the skewness is around 1.14, moderately right skewed, and the normality test is even not significant here, as the p-value is not less than 0.05. And if we see the QQ plot here, we would see the data is tilted towards the up part and tail to the up, which shows that it's rightly skewed. Then we go to the pH one, we could see the skewness is around 0.03, so it's not that much skewed. The data is not normally distributed, but tends to be normally distributed. And even if we go to the normality test, it's less than 0.05, which tells the data is already moderate normally distributed. And then we go to the alcohol data set. From that we could see the skewness is around 0.85. It's not that skewed, but the data is not normally distributed. And in the last we see the draw distribution of the scores. We could see the data is not skewed, not tailed, but the data is not normally distributed. So now after this we'll see how I did the data transformations for the chlorides variable. What I did is a order norm transformation, which is a inverse is a cumulative distribution function, and I took the inverse of that linear rank scaling. Along with that, I used a z-score transformation and used a negation. So from the dataset we could see the normality is 0.02, the p-value, and it's normally distributed and it's not that much skewed. And even if we see the QQ plot, it's almost a straight line, which tells us that data is normally distributed. Then we go to the sulfur dioxide. We see I use a best normalized package using the Johnson transformation, and then in the end I use a z-score for the transformation. From the skewness we could see it's 0.02. From the previous value it was around 5. I've drastically reduced the skewness, and the normality is less than, and the p-value is less than 0.05, which shows the data is normally distributed. And as in the pH one, as the data was already normally distributed and it wasn't skewed, I just used a z-score transformation to bring the values to 0 and 1. And if we go to the alcohol one, we could see that I use a order norm transformation, which is again a linear scaling using an inverse of cumulative distribution function and using a z-score. Along with that we could see the skewness is 0.06 and the p-value is 0.6, and it is a significant value. And in the last we see the scores. For this transformation I have used a log x plus a transformation with a setting as a 4 to make the data look more I would say normalized. And I took a value just to as I was using a log x transformation, and the data was the p-value was not getting reduced, so I tried a bunch of numbers and I came to the conclusion that if I use a 3 it's more, if I use a 4 it's more normally distributed. So after doing transformations and fitting down the models, we could see the error matches and correlation coefficients. If we see, if for weighted average mean model, if I see RMS is 0.15 and the average absolute error is around 0.12, and for OWA model it's 0.16, and if the average absolute error is 0.13, for power mean it's 0.15, and average absolute error is 0.12. From this we can see that the weighted average mean and power mean models are more, the values are more closer to the real values, and even the absolute error is closer to the real value. So if I have to range the models according to the according to in the order regarding the better, I would say I will arrange the models. If I have to arrange the models according to the base, on the basis of error measure, I would say power mean is better than weighted average mean, and the OW is the least better. And even if I see the correlation coefficients, I would say VM and power mean has better one, combining PSN's PM and correlation coefficients. After this discussion, we'll move on which model is the best fitting model, and from what we could see, the weighted average mean, we have seen the RMS is 0.15, and we already discussed the RMSE, absolute error, Pearson, and Spearman correlation. So what we could discuss are the weights which are given to the model. As we could see, the weights are equally distributed with like no weights been giving a lot of priority, almost equal distribution. The model is less biased and the errors are comparatively less. And we will now discuss about the OVA, the weighted average mean. In this we could see the errors are comparatively less. From the RMSE, the model is less biased with with just almost one value not contributing to the data set, and that almost all value contribute apart from the fourth value, the first, second, and fourth value, ignoring the third and fifth variable, and it's giving an unequal distribution. In the end, we'll discuss the importance of the selected variable. So while taking wire as a considerable feature, we would say the chloride, sulfur dioxide, pH, and alcohol play a key value. For a good wine, I need to have a chlorides, like chloride contribute to the wine saltiness and body. So I tend to have less chlorides. For sulfur dioxide is important. It prevents oxidation and help in preserving the wine for a longer time. The pH value is important. It tends to give us the overall taste. The acidity and the basicity is all determined the pH, and how the wine's gonna taste on the palate depends on the pH. And the alcohol is a crucial component depending on the which wine we are using. Its range from 10 to 15% on the basis of wine. So a good wine for me according should have low chlorides, high sulfur, balanced pH, and moderate alcohol value. In the end, we will discuss like I according to my hypothesis, I took the weighted average mean as the best model because the data was equally distributed, it wasn't biased, and everything were given equal weights. So after running down my model, after running down the values on the four features, I came to down that the predicted value came around 7. When I compared it to the raw data having the same inputs around 0.65, 0.73, 21, 18, 3.39, 3.36, 10, and 9.5, their value is around 7. And the data which I took from a model was around 0.75, 40, 3.53, and 8.13, and my predicted value was around 7, which tells the model is predicting the data quite smoothly and accurately. The limitations, like after discussing whole thing, the limitation of weighted average mean is the model is quite sensitive to the outliers. If the data is not normally distributed or some data is outside the quartile range, the model may tend to give errors. The weight parameter play a crucial role, although the weights are equally distributed in this model, but however if there is some bias in this model, or there was a bias towards a certain particular parameter, this model could give me errors, and this model is hugely dependent on weights, and changing a small value of weights, or changing or incrementing or decrementing a small value could bring a larger change in the overall result of